you that if you have to study, uh, you have to basically remove the presentation, come out of presentation mode and look at the nodes also. So that's it. Okay, grid computing. I just mentioning it one more time. This is not in scope at all for us. It's whatever is in scope. That's what I'm including in this PPT. So anything that is related to cloud, it will be relevant for big data analytics. But grid, we don't give importance. Okay. So it basically is a group of network computers. Generally, it's done within the company or one, two, or three companies will join together and set up a grid, and they will share all the resources. Okay, so it's nothing but group of network computers to do. So let's say there are two or three companies are working for some weather modeling projects, like it's listed here. Okay, or for some other project, the companies come together. All right, these days even competitors come together to work on certain solutions. So if they're working together, they need to share the resources. Otherwise, they'll be working in separate domains where accessing data will be a big problem due to security considerations. So they can set up a grid of computers and then they can share the data and work on the project. Okay. Cloud computing, sorry, cluster computing is again, it's a linked computers, but you will have a cluster management software in between. Okay, so it's called a cluster middleware or software, which is basically another software to manage all the requests coming in from different applications and users, like here, from this layer, user layer or application layer, and it will know to which resource, like hardware resource, which storage, which CPU, and so on, that task should go to, or that request should go to. Okay, so it will pick all the resources in a uniform and consistent manner, and also for load balancing requirement. Don't want to load certain servers, certain CPUs more compared to other resources. Okay, so this way it is cost effective, and you have basically it uses something called MPI. So MPI is that I think it's multi-processor interface. I think so. Did I put a note there? Sorry, message passing interface. Yeah. So message passing, you are already familiar from cloud. I hope you studied publisher subscriber, like PubSub interfaces, publisher subscribers, where publishers, one or more publishers will send messages to the subscribers usually through a channel, through an interface. Okay, not directly to subscribers. So that is message passing interface. So you need some message passing interface in between, and that will interface with the applications and the hardware. Okay, so there'll be a lot of load balancing done, not only at the network layer, but also at the at this middleware layer also, because this will have all the information about the resources. High-speed network is just a network which will do its own load balancing when it comes to um, diverting the traffic or handling the network traffic. Okay, so so that is the brief intro or recap as far as cloud is concerned. But whatever you have learned in cloud computing before, okay, those are relevant, but those are still useful. But uh, you don't have to worry about those concepts from exam point of view. For exam, we have plenty of topics in big data itself. Okay, so maybe just a very small weightage for whatever is in the slide regarding cloud, grid, and cluster. Okay, that's all you need to know as far as exam is concerned. Okay, let's move on now to more of big data applications. Okay, so just checking the time. Okay, so anybody used Spark or heard about Spark technology in big data or anywhere? Spark framework. Those who did big data and UG would have heard about it or studied about Spark. Nobody wants to say anything. Okay, so Spark is one good example which uses in-memory computing. That's how it improves the performance. So what is this in-memory computing? So as the name suggests, computing is done in memory, and the results, intermediate results, and even the final results, right? They will be stored in memory until they are flushed out to the persistent storage, like it's shown here. Okay, so most of the calculations, computations, everything will happen in memory, and finally, whenever needed, whenever the data has to be stored permanently, that is for persistent storage, okay, and for further processing by some other application, maybe. After the computation, remember I was telling you about different phases, right? Initial processing, then final processing, then transformation, right? Remember extract, transform, load, or extract, load, transform, extract, transform, load, transform, extract, load, transform, extract, transform, load. Covered all those things in module 1, right? So for different phases, right, the applications may need to go to the persistent storage to get the those intermediate results, or whatever stage may be the results. Maybe final results, they want to do something more with the final results. Okay, so in such cases, the in-memory computing is used. So what is the advantage of this? Advantage is you're basically avoiding unnecessary or frequent IOs. So as you know, IOs are extremely slow compared to your CPU time. Okay, IOs generally take from milliseconds to seconds. Okay, so whereas all the computations using CPU, right, they will take only nanosecond. So think about the speed. So this is in milliseconds, or let's say millisecond, if not second. So whatever computation you do in memory, right, it will be almost 1,000 times, not 1,000 times, a million times. This is 10 power minus 9, this is 10 power minus 3, right? So million times faster, theoretically. So I'll just put 10 power 9 minus 9 for this. So theoretically, like million times faster, if you, of course, with some overheads, because you still need some finite amount of time to access the memory. So you all have studied computer architecture, CPU pipelining, the memory data bus, memory bus, data bus, all those things, computer architecture. So there is still some finite amount of time needed to access memory. Okay, but that's why I said theoretically it's like a million times faster by doing everything in memory instead of doing frequent IOs, which will take a lot of time. All right. Then IO will remember your OS concepts. Any IO task will put the process in block state or wait state. Okay, until the IO operation is done. Even with the DMA, the direct memory access, right? Still the process, whatever was running on the CPU, okay, that will be put in wait state until the IO transfer is done. So basically, it slows down everything. So for this, for that reason, they used large memory cache and memory grid. You can't have very large cache, as you know, there is hardware limitation. But they try to use large memory, or you can't have single chip with large memory. What they use is memory grid. So basically what they do is it's just like distributed systems, where the storage is distributed, CPU is distributed, memory is also distributed. So which means if it has like, if the network has like 100 computers, okay, so each one having, let's say, 8 GB RAM. So you have, theoretically, you have like 800 GB RAM at disposal for in-memory computing. Okay, so with that, they are able to do lots of computations and storage of intermediate results, everything in this memory space itself. That way they avoid IOs. So this will speed up computation, everything, whether they're doing map reduce or any application, mapper processes will complete faster, reducer processes will complete faster, and so on and so forth. Okay, so you need to store the data, of course, in storage, because if the power goes, you will lose data, whatever is in RAM. Okay, so DRAM is volatile. So they, of course, they can use a non-volatile RAM called NVRAM or NVM. But again, you are limited to the capacity of the physical RAM. Again, NVMs, they have to pull in NVMs in this grid. All right. So, but you can't save it there, save terabytes of data in NVM permanently. So for that, you still need to depend on external storage for persistence, and you will have to depend on IO. That is unavoidable. But at least for a large part of time, you are avoiding IOs. So that is the theory behind in-memory. In traditional computing, for every single saving, right, there will be lots and lots of IOs being done. Okay, lots of IO tasks. Like you again go back to your OS days, where processors will have set of instructions or threads. Processors or threads will have set of instructions, and the instructions will be mix of CPU bound and IO bound. That's how the programs and applications are written. It's very rare to find only CPU bound programs, only IO bound programs. It won't be that useful. Even if you write a small C program, you will use some printf, scanf, fread, fwrite, that kind of IO calls, and a lot of other instructions where it will require CPU. Correct? So that is the general pattern of program execution. So there'll be a lot of IOs, processors will be put in waits frequently. There'll be context switch, swapping of processors, all those things will happen, which will slow down. That is done in traditional computing. Even on your laptops and in normal servers, traditional computing is used, a lot of IOs are done. So that's a difference. So let's see. So why do we talk about in-memory computing? But this is old data. It's about, I think it's about 10-year-old data, the statistics. Anyway, it's still relevant. Only thing, some storage, the data that we are handling is exponentially increased. It's much more than this exabytes. Okay, this is I think 1,000 times petabytes. So 16 exabytes of data is old data. 64-bit processors can address. Okay, which means they can still access the memory if it is available. Memory addresses, large range of memory addresses, if that much memory is available. Then, as you know, memory costs have been going down steadily. So we also, like our laptops, we generally go for 8 GB RAM, right? We don't go with 4 GB RAM anymore. It's very rare these days, even on laptops. So on other servers, of course, they go with large capacity of memory, because the cost of memory has gone down. And then 1 GB of memory is also, okay, there's some price details are going down. What else? Memory available, AM software, embedded products, in memory and AM software. Yeah. So there are various other use cases also. Okay, where in-memory computing, IMC means in-memory computing, is often embedded in products and services. Okay, they are also using memory a lot rather than going to I/O. Okay, then in-memory enabling software is available these days. Okay, so for a lot of reasons, availability, price, requirements, everything they use in-memory computing. Okay, so that's about it. And of course, latency is important thing, right? So for real-time analytics, low latency, because you're doing everything, running all the tasks in the memory itself, rather than going to I/O for anything. Okay, so some more details are given. Yeah, some comparison here. So disk-based high latency, slower access, as you know. In memory, faster, lower latency, good for real-time analytics. So like Spark and Hadoop. So we look at both. In this module, we look at Hadoop and MapReduce. So Hadoop and MapReduce still uses disk-based only. That's why Hadoop is slower. That's why Spark was used, or Spark is being used, because it uses in-memory computing. The only problem with in-memory computing is you need large memory grid capacity, so the cost will be very high. Okay, that is the main disadvantage. Will I put it here? No. No, we'll put it. Okay. All right, so we'll move on. So cost is the main factor. Otherwise, it's good. Any comments or questions till now? All right, so we quickly wrap up some examples given. So where in-memory data is used apart from Spark. Yes, there is Apache, Ignite, and Hazelcast. So all these are, you can say, software that open source, of course. They all support in-memory data grids. So read the notes section below. I put it here. Okay. So you will understand the difference between Ignite and Hazelcast. We don't need it for the exam. Okay. So only SAP HANA is included for this course and for the exam. Others are just given for example. So I put some notes here for your understanding. Then Redis is also a simple database. Okay, it's also used as cloud storage. It has dual functionality. It works as a database and as a cloud storage. It also uses in-memory databases. Basically, the databases, everything will reside in memory. SAP HANA, I will talk about it next. Then Apache Spark, we'll talk about it in the next module. Then memory technology, even Intel Optane, they also support memory grids. Okay, so to do a lot of computation in the memory itself. So you need hardware support. So Intel provides that. So what is this SAP HANA? HANA is like high performance analytic application. Okay, it's all used for in-memory computation platform. As you know, SAP is in the transaction. They produce a lot of business software and transaction processing. They are very good with OLTP and OLAP. Okay, so which is online transactional processing and analytical processing. So they for this they have to have they do basically a lot of massively large computing. Okay, where they have to do large computing in parallel. So they need lot of resources. Then they have to do very fast transactions. Okay, SAP deals with so many terabytes of data. Okay, so if you are familiar with this, what SAP does, SAP company does, right? So you will know they deal with large amount of customers, large amount of data, and so on. So they need very quick processing. All right. Then they have other advantage, multi-tenancy, where they can uh, put or include data from different tenants. A tenant can be a customer, set of customers, or a company, or set of companies. Can mean anything. Okay. Generally, it is set of group of companies. So data related to each company can be stored separately, and and what should I say? Basically, you have security also. So there is no security issue when they store data belonging to different tenants and in the same database. What they do is they'll have separate table for each tenant or set of tables for each tenant in the same database. So that's how they'll separate the data from one company to another company. Rarely they use the same table for two tenants. So in that case, they will use row one, for example, for row one or whatever rows, a certain number of rows. Okay, let's say 1 to M for customer one or tenant one. It's better to say tenant because tenant, as I said, can be a customer or a company. Then row M plus 1 to N, for example. Okay, take these rows can be used for tenants two, customer two, like that. That's how they support multi-tenancy. Okay, they have in-memory storage. They are good with both columnar storage and row-based storage, where the data can be stored in columns. So, like for example, if it is an employee record, all the names of the employees can be stored in one column, all the contact numbers in another column, their salary in another column, their date of joining in another column, like that. Row-based storage, as you know, each row will have a record of only one employee. So it will have everything: name, age, salary, date of joining, address, location, uh, department, whatever, anything that is relevant to the employee. So that will be row based. But generally, it is HANA is a column oriented. Okay, I'll just put COL. It's called as column oriented storage. It prefers to store similar data in the same column for faster processing, faster storage, faster retrieval. Okay, so it supports massively parallel processing, ACID compliance. You all know all these things, ACID compliance, all those things. Then it's good for data persistence, real-time analytics, high performance, application development, flexibility. You just read all these things. So there are lots of use cases and benefits of in-memory computing. It speeds up or accelerates ML model training, everything. Enables real-time dashboards like stock exchange application, IoT, fraud detection, personalization, so on and so forth. What else is there? Yeah, the last one is this. So for future trends is there are a lot of applications and framework are going to use in-memory computing. Okay, there is CXL, which is Compute Express Link. They all use high-speed interconnect. So basically, you need support of hardware, high-speed network, and so on in order to access that memory grid. So they also access like CPU grid, memory grid. They have lots of accelerators, everything to make the data flow through very fast. Okay, and then make the data available for the applications. Let's say if it's ML algorithms that they are doing a lot of computation, so you need to make the data available very fast. All right, or some application that is depending upon the map reducer to finish quickly. So mapper and reducer will be running in the memory, and the data will be quickly transferred to the application. You need high-speed network, then you need a high-speed memory bus. Memory buses should be shorter in length, because longer the memory bus length, longer time takes for the data to transfer from source to destination. Okay, all these things, memory center architecture, all these things. So for various reasons, right? So it's really taking a big leap in memory computing. Okay, it's used in real-time data, big data processing, data analytics, AI, everywhere, wherever the latency and IO overhead have to be reduced and wherever the performance have to be improved. Okay, so we'll stop here, and from next class we'll go into Hadoop and HDFS. Any questions? We'll take attendance. So looks like we are going to do online only. I don't know when this classroom issue will be all sorted out. Right now we don't have separate classrooms available. Then you guys have to send a request to HOD if you want to continue to have online classes. Otherwise, not just department, the university, the institution is expecting you to come offline. Otherwise, according to NAC and NBA accreditation and so on, right? Then recognition of your MTech degree could be a problem. So that is the reason they want to do it offline. Okay, so I don't want you to get into trouble later on because you didn't come for offline class. Let's say few students come, then others don't come, then it will be a problem for those students. Anyway, if you want an online class, all of you send a request and get approval, then you will be safe. Okay, so one of you tell Vishwas to send a message to the group, so all of you can request the HOD to continue with online class. So it's up to you. I am okay with anything. Offline class is better because the hands-on everything will be better. Okay, so let's see. I'll just mark the attendance as per this login ID. So Ashwini is there, Chinmay, Dania, Joshika, Meghana, Nandita, Praveen, Reena, Sabrine, Sheila is missing. Oh, Sheila is there. Okay. Sheila is there. I think Shilpa is always missing. Then Soundarya is there. Okay. Srinidhi there. Soundarya, Sri Narahari. Okay, 1 second. Sri Narahari is here. Then Surya. Okay. Triveni. Okay. Vishwas. Okay. So Saujanya is missing. Srinidhi Krishna is missing. Tejaswini is missing, surprisingly. Tejaswini is also missing. Okay. So I'm done. Any queries, questions from your side? All right. We will close it on time then. All right. Thank you. See you tomorrow. Bye.
Thank you, sir.